All right, so at this point, everybody is ready to learn the rest of the other trig functions. Other trig functions. Because we previously learned about the sine function and the cosine function. And so now, for the other trig functions, let's come up with the first of all tangent, and here's the formal name, tangent. And so, given an angle theta, then tangent has a shorthand abbreviation tan, like that. So tangent as a function, tangent of theta. So tangent of theta, as a definition, equals sine of theta over cosine of theta. And so we simply keep that as a definition. So here's tangent of theta. Besides the tangent function, there's also a cotangent. And cotangent has a short name, COT, stand for cotangent. And for any angle theta, cotangent of theta equals cosine of theta over sine of theta. So these are the fundamental definitions of tangent and cotangent. And then after cotangent, there are times where we're studying the secant function. And secant is defined, and the notation for secant is SEC. And so secant of an angle theta is defined to be 1 over cosine of theta. So these I'm giving here are completely definitions. And the last one on our list is going to be the cosecant. So cosecant, the symbol for that is S, it's CSC. So cosecant of an angle theta equals, by definition, the ratio 1 over sine of theta. So if we now putting together as a comprehensive list, then from the beginning we learn about what sine of an angle theta is. And then next we learn what cosine of an angle theta is. And then we spend a few days or maybe a week to do exercises and getting to know sine and cosine. And then now we're starting to learn into tangent of theta. And then after tangent, we just now looked at cotangent of theta. And these so far has been given as definitions strictly based on the definition based on sine and cosine. And so secant of theta. And then cosecant of theta. So all of the trig functions we ever have to learn here are these 6 trig function right here. But really, in the way how I see trigonometry functions, that these 2 functions, sine and cosines, are the most fundamental because the rest of them came out being built on top of these 2 functions right here. So for example, again, tangent you saw previously in the definition was defined as sine over cosine. And cotangent was cosine over sine, and secant is 1 over cosine, and cosecant was 1 over sine. And then there are many tricks and tips and tricks out there for the, students to remember these, and they're all over the web. So I see there's no need to deliver that here in this video lecture. But so now immediately, let's look quickly at the quick relationship between tangent and cotangent here. All right, so cotangent, we've learned that for any angle theta, cotangent is defined to be cosine of the angle over sine of the angle. But we have learned at this point, when you're taking trigonometry, when you're learning trigonometry, then you must have had enough algebra to understand that now if we're taking this cosine of theta over sine of theta as a fraction, then we have our rights to, sometimes we can see this fraction here as 1 over sine of theta over cosine of theta. I mean, for now, I'm doing nothing but just making the fractions a little more complicated, but there's a reason why. So the same fraction from the beginning here, cotangent is, by definition, cosine of theta over sine theta. But that fraction can furthermore be understood as sine theta over 1 over the fraction sine theta over cosine theta. But hey, wait a minute. This sine of theta over cosine theta is the same as a tangent of theta in the denominator, and that 1 in the numerator is there. And so it's worth a little bit. It's not a big discovery, so that we can call it it's an identity, but it's always true, and we refer to this. So cotangent, something worth to remember, but cotangent can also be understood as 1 over tangent of theta. So it's another way worth to remember. I would say this is something to remember. The reason I pointed it out that cotangent of theta can also be understood as 1 over tangent of theta, because how about wait for me to finish with writing down a couple other ones right here. But secant, we also learned through the definition that secant of angle theta, any angle theta, is 1 over cosine of theta. And the last one in our list that we just looked through the definition was cosecant of theta to equals 1 over sine of theta. So if we put all these three functions together in a list and looking through them together, one thing they have in common, it looks like they're the reciprocal of some other functions right here. And then not to mention that, so since cosine theta can be understood as 1 over tangent theta, then you can also understand tangent theta as the reciprocal of cotangent. But usually not too many people see tangent theta this way. They more into taking that definition of the tangent theta being sine over cosine. So leaving that out, then putting these three functions together, they're all in a form of being a reciprocal of some other known trig function. And so there's a reason why sometimes this is the reason why sometimes you might hear people refer to these functions as these are the trig reciprocal function. All right, and let's now do some really basic examples right here, because I would like to save the more advanced examples in other videos separately for those other advanced type of problems. Yeah. But so in this very basic example here, well, let's stay with some of the straight old calculation problem. So here's my example. Let's say we want to evaluate And about first problem in this, and so evaluate means which is gonna, come out with the final output value. And so how about tangent of the pi over 3 angle? Okay, and so the reason I brought up these very basic one, but surprisingly they can start getting a little tedious work sometimes, but I need to bring this up so that you get into that good routine, that good habit of anytime you're evaluating these functions, bring them back to the original definitions. Tangent is defined to be sine of a pi over 3 and cosine of a pi over 3. And then the work here turns out, and now we have already done a lot of exercises and examples for finding each of these individually. So on a unit circle, so sine of pi over 3 is that angle, is that angle 60-degree angle. So the vertical y coordinates on that in quadrant 1 is, and on the unit circle again, square root of 3 over 2. So that's sine of pi over 3, and cosine of pi over 3 is a 1/2. So we need to simplify this fraction right here. So we got a fraction on top of another fraction. So the rule of working with fraction, now we can take the numerator fraction and multiply with the reciprocal of the denominator fraction. So here that denominator 1/2 here becomes a 2 over 1, but now the fraction, the division here turns into a multiplication. And so the common factor in both numerator and denominator got cancelled out, and here we left behind with square root of 3 over 1, which is ridiculously easy enough, square root of 3. So tangent of a pi over 3 angle, of the pi over 3 angle, is square root of 3. And so here I just need to make a note right after this example here. So remember how I talked about anytime we're working with sine theta or we're working with cosine theta, then the output value of these two functions, regardless of which angle theta we're working with, but the output value for sine and cosine function can only be anywhere from -1 is the least to 1 is the most. Same thing with cosine. -1 value is the least, negative, and here is the 1 is the most. But just because we have sine and cosine values, and the way it is being restricted, the output value being restricted in between that interval for sine and cosine, doesn't mean tangent is going to have that restriction naturally. And so, as a matter of fact, if we look back into that example we just immediately finished, then tangent of pi over 3 came out being square root 3 after our example, and this is already way above 1. So something to note about, but it's not too important that you have to remember and nail that down for now. And so let's do another one. So here let's look at how about secant of the angle pi over 4. And so this, once again, starting out, it's always good to rewrite the secant expression here by its own definition. So 1 over cosine, and that's what secant is defined as, 1 over cosine of the same angle. So here's pi over 4, so 1 over cosine of pi over 4. And so cosine of pi over 4, we've learned that it's square root of 2 over 2. And we put it there in that denominator. And so our work now turns into a 2 over square root of 2. And 2 square root of 2 can be thought of, well, 2 can cancel with square root of 2, and that gives us a square root of 2 here. Okay, and if you need some clarification here, then the 2, this can be thought, the 2 here can be thought as a square root 2 all square, and we're dividing that by a square root of 2. And so canceling out that. Square is gone. That's why we ended up with that square root 2 again. And in a different example, what about, let's put up some negative angles to see how things work. So how about cotangent of a negative 2 pi over 3? And so right at start, straight out from the definition, cotangent is defined as a cosine of the angle negative 2 pi over 3, and dividing that by sine of the angle, same angle, negative 2 pi over 3. And so cosine of a negative angle 2 pi over 3 gives me a negative 1/2, because the angle negative 2 pi over 3 lands right into the third quadrant. And then sine value of that angle negative 2 pi over 3 is the same as negative square root 3 over 2. And so now once again, let's do some fractions here. And so what we have is and negative cancel with negative, and let's multiply by the reciprocal. So we have 1/2 times 2 over square root 3. And so canceling out a common factor 2 in numerator and denominator, there we're looking at 1 over square root of 3. And then we need to rationalize the denominator. So the denominator here is a square root of 3. I am going to multiply another square root of 3 to the denominator. But then in the rule of working with fraction, anytime you multiply one expression, one quantity to the denominator, you must multiply the exact same to the numerator. And so here I got square root of 3 there. And so that's the standard step of how we can do rationalizing the denominator. And so that gives me my final answer here, turns out being a square root of 3. Square root of 3 times square root of 3 in the denominator here is a 3. So our cotangent of this angle negative 2 pi over 3 turns out to be square root of 3 over 3. All right, so dangerous. So before we advance on further into the quarter, I gotta point out a couple dangerous mistakes that I commonly see in many of my students in past quarters, and I'm sure some of you, if you don't watch this carefully, you're gonna make that similar mistakes again. And so as we now start, the reason I never mentioned this until now is that as now we start talking about tangent, for example, being defined as a tangent of any angle theta, being defined as a sine of theta over cosine of theta, we start encountering into those kind of expression where you have the sine of theta over cosine of theta, and here's what people commonly mistake. That's where it happens right here. People that I have seen commonly cancel out the theta away, so and consequently ended up with sine over cosine, and without the theta indication. So now I have to really and kindly remind everybody, without the angle, then sine here is a meaningless expression. So it's not even a quantity, it's not even a number, it's not like a 5 or 10 or whatever, it's only a name of the function. So without theta, then this we can't even proceed with that the symbol over here. The same with cosine. If we're writing a cosine but skipping the angle theta indicator, then we can't even work with that problem. So I probably see the reason why people in my classes, or I've seen many other students commonly cancel out that theta. It's probably because they think that there was a multiplication there existing between sine and theta. And so once again, just to remind everybody, and please highlight that for me, but sine by itself is not a quantity. It's not an expression, not even an expression. It's only a symbol to indicate that we're looking at the sine function. And so it will become meaningless without the angle theta. So please never cancel away your angle theta expression in there. And so that's the number one mistake that I commonly see. And then along with that mistake, similar to that mistake, because many other times I see people say, for example, they write the the fundamental identity, the Pythagorean identity. Like sine square plus cosine square equals 1. And so once again, the mistake here is similar. People are skipping the angle indications. And so I need to remind everybody again, sine itself and cosine itself, they are not quantities. So if you're writing sine square, it makes no sense, and it's cosine square, it makes no sense. And the worst now is adding these two squares to make them equals 1. It's completely meaningless, because what's happened here is that sine needs to always come with an angle indicator. You can use either an x or a y or a theta, whatever your variable's name, but you gotta have an angle indication in there. Otherwise your sine function is not going to work. And then throughout the quarter, I will be pointing out other mistakes, other dangerous habits that that highly recommended that you stay away from. But for now, let's just call that these are about all we have for now. And now we are ready for looking at what about we're outside of the unit circle. So remember that my approach to explain the sine and the cosine function was that I approached that as something that came out from the unit circle. But at the end of my discussion there, at the end of my lecture there, I also discussed that there are now times that you need to work on a circle that's no longer the unit circle. For example, those circles where you got a center still, center at the origin, but the radius now is no longer 1. And so we're still going to have a terminal point here. Okay, and that terminal point simply is just being treated as some coordinate points on the plane there. And so tangent theta, let's give a new look for each of these other trig functions right here. So tangent of theta is definitely defined as sine of theta over cosine of theta. But in that way, sine of theta, remember that when we're actually outside of the unit circle, then sine of theta is the same as, is defined as y over r, which was, so I need to remind everybody, but sine of theta outside of unit circle on any other general unit circle, radius other than 1, then defined as y over r. And so here sine is y over r, and cosine of theta is equals to x over r, similarly. And so a little bit of math here, it can turn it into y over r multiplied with the reciprocal r over x right here. And here we can cancel out the r common factor. And so now that turns out that tangent of theta when we are outside a unit circle can be related to the x and y coordinates as a ratio like this, y coordinates over x coordinates. And that's how we come up with a different way of looking at tangent theta right here in terms of those x and y coordinates of the terminal points. And so now for the other trig functions, then I don't have to go as detailed anymore in terms of how they get derived, in terms of how they come from, how they arrive at these new look right here. But so for cotangent, then related to the x and y coordinates as x over y. Your secant function, secant of theta, is relate to the x and y coordinate as the radius r over x. And the last one here, cosecant of an angle theta, is relate to the x and y coordinates as r over y. And I have to constantly remind everybody that the angle theta we've been talking about is, let's say now you're outside a unit circle, which is looking at some coordinates point here, then the radius is from where the terminal point is back to the origin, but angle theta is here. that angle, that famous angle, the central angle that it's the terminal point made with the positive x-axis. All right, and so now let's look at some further details, in which is also the last detail need to be mentioned in my video lecture here. But so let's say given an angle theta anywhere on a unit circle, then we already learned throughout the beginning lessons about sine and cosine of the angle theta is that sine square of theta plus cosine square of theta equals 1. And so it was an identity because it's true. It's this identity here, this relationship here, this equation is true for all values of theta. It doesn't matter where you add on a unit circle, sine square of theta plus cosine square of theta must always equals 1. So majority of people out there refer to this as the Pythagorean identity. But if you recall from my earlier video lessons that I actually refer to this identity here as the fundamental identity here, because and I couldn't point out a reason why I was calling it that way in my earlier lecture, but in this lecture I'm starting to be able to explain why it's so fundamental in the way how I see it, in the way how I view it. So all right, so let's start out with our Pythagorean identity here, and let's just pretend that we're going to be doing some work around. It doesn't have to be a formal proof or anything like that, but let's just explore around the idea here. But sine square plus cosine square of theta equals 1, and so being an equation, we have our choice to divide both sides by an expression. So that's just the rule for an equation, so we can always divide both sides by an expression. So this time I made my choice to divide both sides by cosine square of theta. And so dividing both sides by cosine square, then for now I'm going to leave the right hand side to remain the same, cosine square of theta. My left hand side I'm going to turn that as, you can see that now we have a fraction, two terms in the numerator, so we can break it down as sine square of theta over cosine square of theta, and then plus, here I'm looking at cosine square of theta over cosine square of theta again. So in the next step, you can see that quickly this can be reduced down to 1 right here. And so yes, indeed, in the next step, cosine square theta over cosine square theta reduces down to 1. I'm still leaving this right hand side the same way, nothing much to be done. But then sine square of theta over cosine square of theta, how about we can purposely remind yourself that sine square is just the way we're indicating it, but it's sine of theta all being square. And so the two squares, the two square power in a fraction, we can rewrite it as sine of theta over cosine of theta, but all square. And so now that starts making it more clear about where I'm going right here. Sine theta over cosine theta, we just now know that it's the same as tangent of theta. And so, but here in this thing, having that square, then it becomes a tangent square. And then tangent square plus 1 equals, let's have a look at our right hand side at this point. So 1 over cosine square, the same thinking process as that earlier, the same reasoning as that earlier, that can be thought of as a 1 over cosine theta, but all square. And so now 1 over cosine was previously defined as secant of theta. And so now taking account together with that square right there, we actually came down to secant square of theta. And so what we have found here is that we came up with another identity. This other identity we just came up with is being part of the Pythagorean identity right here. So as a matter of fact, Pythagorean theorem, Pythagorean identity refers to a whole big family of identities out there, and this one here is one among them. So it's another important identity we just found. Also an alternative name, an alternative form of identity of the Pythagorean identity, but it's primarily the relate between secant and tangent. But see, so my point of saying how fundamental this sine square plus cosine square equals 1 was, because this is the ground where many other, and you can see throughout my my later times in the quarters right here, this identity, once we've learned it, this is the ground where you can grow a lot of other identities out of that. All right, and so I'm going to do a similar work, starting out with my fundamental identity, sine square of theta plus cosine square of theta equals 1. And so this time I'm going to choose to divide both sides. I made my choice to divide both sides of my equation here by sine square of theta. And so sine square of theta, once we divide it into both sides, the left hand side now will become 1. And as you have seen some experience through my earlier deriving work in here, I can start picking up pace a little bit. But sine square over sine square here is 1, and the other cosine square over sine square, well, then we got a fraction here, cosine square theta over sine square theta, and all that here equals, right hand side is the same as 1 over sine square theta. But so cosine square over sine square theta is the same as similar arguments with how I was doing the tangent, and here we're looking at cotangent square of theta and plus 1, and then this left hand side here is now done. The right hand side, you can recognize that being cosecant square of theta. And so what we have found here is another identity. It's another family of the entire big family Pythagorean identities out there. And so for that, and once again, this thing grew out of that famous, fundamental identity, sine square plus cosine square equals 1, like that. And that's the reason why in any time I'm leading a trigonometry class, I've always been mentioning to my students, this is the fundamental identity in trigonometry.